Everybody, so my name is Yingcai Zheng. I'm a professor at the Earth Science Department. I'm also director of Rock Physics Lab. So today I'm going to share with you some technical progresses we have, because I believe eventually we depend on the breakthroughs and the progress in technology. So with Utah colleagues, actually we have many years of collaboration already, and I hope we will have more collaboration in the following years. So these are 4 papers we published in the last 4 years with Utah Forge people, Joe Moore, Clay Jones, and Phil Wanamaker. So this is this year's paper about seismic anisotropy of granite rocks from the stimulation well at Utah Forge. I'm going to talk about the main findings in this paper. We have another paper, also EGS, Utah Forge, about using the shear wave splitting to measure the anisotropy in the reservoir. And this one is using the Utah Forge DAS data. We found some very interesting observations. I'm not going to talk about the findings here in this paper. That's a previous work about elastic waveform inversion at Raft River geothermal field. So this is my group. We have about more than 10 people, like 12 or 13 people. Most of them are students. Also, they are young students. The oldest student is third year, so fourth year. So also we have very active collaboration with research professors. I'm really happy to see that DOE, NSF, and some companies recognize the value of our work, so they provide the financial support. So what do we do here? So we focus on geothermal fields. Some of the technology actually is, can be used in CCS too. So as we know, the heat, fluid, permeability are the 3 very important elements in geothermal fields. And the permeability largely provided by fractures. So our research is centered on fractures. So we worked on both hydrogeothermal and EGS, and also rock physics. So in the hydrogeothermal, you don't see a pointer, okay. Oh, here, okay. So the challenges we try to solve is find a new heat sources in the hidden geothermal systems. Jim Fald's group, they published some papers. They said more than half of the geothermal resources are hidden, which means no surface expressions. So how to find those hidden resources is a challenge. Second one is we want to also find a nearby hot resource for existing power facilities. For example, in Nevada, some places the geothermal power plant have been operating for decades and the temperature is going down. So they need to find a new wells to drill to extend the lifespan of existing facility. So in this domain of research, our work is focused on imaging fractures and infer permeability using seismic data. So this seismic data include the surface seismic data and also subsurface seismic data. The other one is EGS, Enhanced Geothermal System. This is about emerging or future technology. So we focus on a new phenomenon discovered in my lab, which is called the pressure surge effect of fluid field fractures. So what it says is a fluid field fracture can act as a pressure amplifier in the subsurface around the fracture. So if you can locally enhance the pressure, you can develop a pressure gradient which can drive the fluid to flow. And this phenomenon can also be used to control fracture growth and stimulate permeability. Okay, this is about some future technology. And in rock physics, we do lab experiments. We measure the response of the rocks at different frequencies and also at the different pore pressures. So all this work, we focus on the value of seismic signals because a lot of the geothermal depend on EM and other type of technology. Not much about seismic. Seismic is usually used to monitor the reservoirs. So here I want to emphasize that using seismic, we can delineate the fracture network also to control the fracture under the subsurface fluid. So first part is hydrogeothermal. Jim Fald's group laid out some geological settings for exploring geothermal resources. Mainly these places you have extensional tectonics, so which means you can open fractures. The fluid can flow through the fracture. So our work is using the seismic. This time is the surface seismic. We can find the larger scale faults and the small scale fractures. Even in the Utah fault cores, we see a lot of small scale fractures in the cores. And then we can find the faults using AI, machine learning, and the small scale fractures. Those are like 10 meters in scale, orientation, density, compliance. You can optimize your reservoir for energy production. So everything is rests upon what is a fracture. A fracture is a broken surface, maybe with a certain width. We use this compliance model. So basically, you apply a pressure across the fault, across the fracture plane. You can increase the width of the fracture or the aperture of fracture a little bit, which is d meters over the applied pressure. You get a displacement over applied stress, which you get meter per Pascal. So this number, this ratio is called the fracture compliance. And we found that when the fracture compliance is large, so which means you can easily open close the fracture, you can see large seismic wave scattering coefficient of the fracture. On the other hand, researchers at Purdue University, they found this graph, so which means if you increase fracture compliance to the left, because originally they used the stiffness, which is inverse of fracture compliance on the x-axis. So if you increase fracture compliance, the flow rate increases. So basically it means compliant fracture, more flow. Previous slide, I showed that compliant fracture, more seismic scattering. So this provides a link to use seismic data to probe or infer fracture compliance, therefore the flow. Okay. Using seismic data to get the fracture distribution in the subsurface, we partition the reservoir into grid, essentially boxes. For each box, it may or may not have fractures, but we can shoot a directional beam. It's like a laser beam down to bombard this fracture unit. So the wave will interact with the fractures, create interference pattern observed at the surface. So basically, we just need to map this observed interference pattern to the subsurface fracture network geometry. And this can be done using a neural network. This is nothing magic. Even without it, we can do it. But with it, it's just more convenient using the already large amount of infrastructure in the AI community. So basically, we take the interference pattern on the surface, we produce the subsurface fracture distribution. We applied this in Soda Lake. For people who work in the geothermal, you know this field. It's been operating more than 40 years. And this is the surface seismic source receiver distribution. It's about 6 kilometers, more than 500,000 seismograms. So here is the model. So In the subsurface, there's a basaltic body, extrusive basaltic body. And there are two exploration targets above the basaltic body and below the basaltic body. So above the basalt, we found that there are 4 regions with very large compliance values, so which is this spot, this spot, this spot, and that spot. So this is about 250 meter depth. And we can slice down, we can move down to a deeper depth, 300 meters. We can still see this spot persists. And then we presented this data to our findings to the company. And we were told, oh, there is a steam cap in this P0 region. And now they are trying to drill well around here. And this steam cap was confirmed by previous drilling. Okay, so that's a small scale fractures around a 10 meter scale. We have a new technology to delineate them, and this one is about larger scale faults. In the afternoon, you will see a poster, Joe McNeese poster about this. The second one is a new phenomenon called the pressure surge phenomenon for fluid field fracture. The first paper published 2017. The objective of this newly observed phenomenon we want to do is we want to create a localized pressure amplification which develops a pressure gradient which can drive fluid flow in the subsurface. So this everything is remote. So the second one is we want to use this phenomenon to control fracture growth. So you can frac the EGS reservoir, but in the meantime, you can control the fracture length and the width. So the idea is here's a rock, here's a fracture, and there's some fluid here. So if you perturb the fluid pressure at point A, what is the pressure at point B inside the fracture? The Pascal principle says they are equal. So if you have changed the pressure by 1 Pascal here is going to be 1 Pascal. But Pascal principle is a static principle. But when you have dynamic phenomena involved, so which means if you perturb the pressure at a certain frequency, and if you measure the pressure change here, you can actually get a very large amplitude. And this is called the pressure amplification effect. And I can take the ratio of the amplitude of the pressure inside the fracture and the stimulant pressure outside the fracture, define an amplification factor. We published this theoretical paper in 2017. Then later we did the experiment at UH AGL facility. So basically we found there is a 25.2 times amplification. So this is very exciting because in theory we should be able to achieve amplification factor of more than 800 times. So basically it's like a lever rule. So you can have a very small perturbation but can achieve a very large pressure change inside the fracture. Here shows some pictures about the setup. And here, because the fracture is very thin, we have to make a very small sensor to measure the pressure change. So we made a sensor which is 0.2 millimeter thick. So we can directly put the sensor inside the fracture to measure the pressure during the wave propagation. Third part is rock physics. How am I doing on time?
2 minutes.
2 minutes, okay, good. Third part is rock physics on Utah Forge core sample. So with Clay Jones and Joe Moore, we got the rock core samples last year, September. They performed a lot of characterization work on the rock, including CT scan, mineral analysis. We found micro cracks in the granite. And then we performed in our lab anisotropy measurement. We found if you increase fluid injection, if you start to inject fluid, the pore pressure will increase. Increase the pore pressure can increase seismic anisotropy more than 20% in both P wave and S wave. So this really provides some guidance on how to conduct seismic monitoring to track where the fluids are in the subsurface, because you can observe the anisotropy. This is a course we got from Utah. Here's the reservoir. I'm sure you will see this picture more later. And here the workflow, we did the sample preparation, mineralogy, ultrasonic measurement, fracture analysis. Okay. And then we conduct anisotropy measurement using our equipment. We conduct 1 megahertz anisotropy, ultrasonic wave measurement. This is the main result. So if you increase confining pressure, or basically if you move to the left, it's going to be increased pore pressure. The anisotropy will increase. So you can see a very nice line. This is a 5 megapascal. The right side is a 50 megapascal. So the P wave anisotropy, 23%. So this is very, very strong, and which is good because that it means we can detect it. To summarize, fractures are very important in geothermal fields, and they're also important in CCS. Actually, I have another DOE project working on site selection for gigaton storage. Basically, we detect faults and the fractures. And we have a novel method to image faults and the fractures in geothermal fields. We also applied to the Salt Lake geothermal field. And in rock physics work in granite, we found injection of fluids can increase pore pressure, can increase anisotropy. And this anisotropy is very strong, more than 20%. The other thing is we're working on another paper. So because we did a mineralogy analysis, we found only using the mineral composition, we cannot explain the measured anisotropy. So that means the fractures must play a role. So we have done the work. We're in the process of submitting the paper. And finally, pressure surge phenomenon. This is really an ongoing and future research topic. The goal is to show that how we can activate local pressure gradient to drive fluid flow through the subsurface. So this is really engineering the fluid flow in the subsurface. And we also want to use this effect to control not only fluid flow, but the actual fracturing process and the growth pattern of the fractures. So thank you very much.
Thanks so much, Yingcai. So as we get ready for the next talk, if there's Brian come up, there's a quick question for Yingcai. We might have time to have that answered.